Hello dear students, in this lecture we will discuss about what is a microcanonical ensemble, and we will provide you the definition how we can write the complete definition of microcanonical ensemble, and then we will discuss about its application, and we will talk about the classical ideal gas problem to find out the various macrostates for this microcanonical ensemble, and then we will discuss about the harmonic oscillator problem. So let us start. So starting with the definition of this microcanonical ensemble. Now, as we have discussed in our previous lecture, the macrostates for this microcanonical ensembles, they are defined with this N, V and E, and all these three macrostates they are considered as constant. Now, it is preferred to specify the range of energy values. So, let us say we will specify the range for this E minus delta by 2 to E plus delta by 2, rather than having a sharply defined value of E, because any type of system, either this microcanonical ensemble, it is completely a isolated system, but some sort of energy it is being lost from this system to reservoir, and we cannot sharply define that the energy it is always remain constant for this particular microcanonical ensemble. So we define this range of energy values for this microcanonical ensembles. So there is a choice for the systems of this ensemble to be in any one of this larger number of possible microstates, and we will consider the representative points in an ensembles. So they lie anywhere within this problem of hypershell. So the microcanonical ensemble we can define as is a collection of system for which the density function, so density function we generally represented with this rho, which is dependent upon this position and momentum coordinate, and the value of this density function, it is considered to be constant for a particular phase space trajectory of the hypershell, and for that particular hypershell the value of energy, so it is somewhere like lie between these two energy limits. So E minus delta 2 to E plus delta 2, and all the other values if it is excluding this energy range, and we will consider all those density function as equal to 0. So what does it mean? So it means that the representative points they are uniformly distributed over this relative region of phase space who is having this energy range, and the expectation value of these number of representative points, these are in a particular volume, so that is the confined volume d omega. So in this relevant hypershell of phase space, and this volume which is directly proportional to this delta omega, which is the volume of this confined space. So from that we can say there can be a connection between this mechanics of this microcanonical ensembles and the thermodynamics of the member systems which are present within this ensemble. So there is a fundamental volume which we generally consider as omega naught, so which can be regarded as equivalent to 1 microstate. So this is the volume of 1 microstate. So since there are let us say many number of microstates, and that is represented with this sigma, which is dependent upon this value of n, v and e. So volume corresponding to sigma microstates which are present in this micro-canonical ensemble, so that volume is generally considered as omega, and volume corresponding to one microstate which we generally considered as omega over sigma, and that is generally considered as the omega naught. So that is the volume of one microstate, so that will be equal to omega over sigma. So therefore one microstate it has volume of omega naught, and this is sigma microstate it has volume, so we can write it somewhere like in this form. So that is the volume of sigma microstate over volume of one microstate. So the thermodynamics which can be calculated by following or by calculating the value of this entropy which is dependent upon these microstates NV and E, and this derivation we have already derived in our unit number 1, and on the basis of this how many number of ways how these the systems within this micro-canonical ensemble they are exchanging, so all those microstates, so that is equal to S which is equal to K log of omega. So the basic problem here is we need to calculate the value of this omega naught. So we need to find out the value of this omega naught, and once we find out the value of this omega naught, and from that we can find out the total volume, and from that we can find out the total number of microstates which are present in a particular energy value or for a particular case. So the value which we will derive in our next article, so that is the application of this micro-canonical ensemble for the classical ideal gas, and it should be of the order of h cube, so that is for a n-dimensional system, and so this we will derive in our next lecture. So let us start our first example of a classical ideal gas. So we will do two examples for this micro-canonical ensemble, and this is example number 1. Now this classical ideal gas, it is composed of monatomic particle, so that is having a single atom, and in the micro-canonical ensemble the volume which is generally defined with omega, so the volume of this phase space accessible to these representative points, so that is generally given as, so integration of this one, and that is dependent upon this phase space trajectory which is dependent upon this position and momentum coordinate for the 3n dimensional 3D for 3D problem. So this integration it is generally dependent upon this prime factor, and this integration it is restricted by conditions. So it is restricted by two conditions. So the first condition is the particles of the ensemble system, they are confined to volume V. And the second restriction or the second constraint which we will apply for this volume is the total energy of the system, it lies within the limit. And what are those limits which we have already defined? So that is the energy it is not having a sharp value, and the energy it can vary between this finite value which is equal to delta. So we need to find out the Hamiltonian for this case, which is a function of pi alone, and the integration over this qi, that is along this position coordinates, it can be carried out straightforward, and the value of this volume, so we can write out the position and momentum coordinates separately. And this position coordinate for this phase space trajectory, that will be of the order of the volume which is confined, and this integration that is dependent upon this dp3n, where dp is the change in momentum, and this integration it is applying within the limit, so that is from e minus delta by 2 to e plus delta by 2. So we can write it here clearly. So our equation becomes e minus delta by 2, and energy, total energy, which is equal to pi square over 2m, where I which varies from 1 to 3n, and it lies within this limit e plus delta by 2, and this value, so this is the prime value where our integration which lies within this limit. So solving for this case, so let us say, so we got this value of this total volume, so v raised to power n into I1. So let us say this is equation number 1. So we need to solve this value of I1. So we will solve it separately. So I1 is equal to volume of 3n dimensional hypershell bounded by two hyperspheres of radii 2m e minus delta by 2 under root and 2m e plus delta by 2 under root. So it is something like, so we have this phase space trajectory, that is the complete volume, and the value of this energy, so it can vary for this hypershell within this range. So that is the inner value which is being changed. So this is our Hamiltonian function which is dependent upon p and q, and it is dependent upon e minus delta by 2 to e plus delta by 2. So within this range it can exchange some sort of energy for this small value of energy from e minus delta by 2 to e plus delta by 2. So this volume, so that is dependent upon the thickness of the shell multiplied by surface area of 3n dimensional hypersphere whose radius is of the order of 2m e under root. So in order to find out the value of I1, we need to find out two values. We need to find out the thickness of this hypershell, and then we need to find out the surface area of this 3n dimensional hypersphere. So let us first calculate the thickness of this hypershell. Now the value of delta which is being changed, so that is very less as compared to the E value of our microstate. So the thickness of shell, so it can be calculated 2m E plus delta by 2 minus 2m E minus delta by 2. So this value is between these maximum value and minimum value of this thickness of our hypersphere, and we can solve this. So by taking 2 under root 2m as common, so this equation become e plus delta by 2 the power 1 by 2 minus e minus delta by 2 power 1 by 2. So taking again e as common, So this equation comes out to be 1 plus delta over 2e is to power 1 by 2. So if I keep this within the bracket, and this comes out to be 1 by 2 minus, again if I keep within this bracket, 1 minus delta over 2e 1 is to power 1 by 2. So now this e is common in this both equation and it is under root of 2, and we can keep e outside, so this equation becomes under root 2 me, and within this bracket this becomes delta over 1 plus delta over 2e under root minus 1 minus delta over 2e bracketed under root. So applying the binomial theorem, so we can solve this value. So this thickness, it comes out to be of the order of under root 2 me, and when we apply the binomial within this bracketed term, so we can write it something like 1 plus delta over this under root goes to the denominator, it is 1 plus delta over 4e minus of 1 plus delta of 4e, and you can see that, so this 1 and 1 they get cancelled out, and what we left with is under root of 2me into 2 delta over 4e. So the thickness of this hypershell, it comes out to be of the order of under root m into delta over under root of 2e. So this is, let us say, equation number A. Now we need to find out the other value, that is we need to find out the surface area of this hypersphere. So we know that for n-dimensional sphere, volume, it is of the order of pi n by 2 k raised to power n over n by 2 factorial, and similarly the surface area for n-dimensional sphere, so that is equal to 2 pi n by 2 k n minus 1 over n by 2 minus 1 factorial, or gamma function. So taking this value of surface area, so surface area of 3n dimensional sphere of radius under root of 2m, so putting the value of this r, that is of the order of under root of 2me, so over this equation, so this comes out to be Sn, that is 2 pi, so here that is for this n dimensional, and if there is a 3-dimensional sphere then this powers, so it comes out to be 3n by 2, and r, that is 2m e under root 3n minus 1 over 3n by 2 minus 1 factorial. So this is our equation number B. So putting the value of this A and B, and in order to find the value of this whole integration term I1, so I1 comes out to be delta under root of m over 2e multiplied by 2 pi 3n by 2 2me the power 3n minus 1 over 2 over 3n by 2 minus 1 factorial. So this is the value of I1 and the volume of this total hypershell, that is omega, which is of the order of Vn into I1, and putting the value of this I1 in this equation. So our volume of total volume of this hypershell, so it comes out to be V raised to power n delta over m over 2e under root 2 pi 3n by 2 2me 3n minus 1 by 2 over 3n by 2 minus 1 factorial. So let us say, so this is our equation, so that is, you can say that is equation number 2. So once we find out the value of this omega, from that we can find out the microstates of the parameters for this microcanonical ensemble. So this omega, we can write it something like the summation, that is the number of microstates n, v and e. So this comes out to be v over h cube raised to power n 2 pi me raised to power 3n by 2 into 3n by 2 factorial. So this we have derived when we have discussed the classical ideal gas problem in our unit number 1, and the microstates we have defined or we have derived for this classical ideal gas, and it comes out to be this equation. So let us say this is equation number 3rd. So from that we can find out the change in energy value, that is from E minus delta by 2 to E plus delta by 2. So the new microstates, which is dependent upon this 4 parameters N, V, E and delta, so that we can calculate by differentiating this summation with respect to E. And when we derive this equation, when we have already solved this value, so which comes out to be V over h cube raised to power n over 1 over 3n by 2 factorial multiply by curly over curly E. So that is 2 pi me derivative the power 3n by 2 with respect to E. So when we solve this, so this comes out to be delta V over h cube raised to power n over 3n by 2 factorial. So when we solve this derivative term, so this 3n by 2, it comes here. So we can write this term within the bracket 2 pi me. So this becomes 3n by 2 minus 1, and again taking the derivative of this internal term, so that comes out to be 2 pi m. So from that you can see that, so when this 2 pi me, this goes in the denominator, so I will write it here. So this new microstates, so it comes out to be delta V over h cube raised to power n over 3n by 2 factorial. So 3n by 2, and when we solve this, so this equation becomes 2 pi me 3n by 2, and the 2 pi me minus 1, so when it comes into the denominator, so that is 2 pi me, and this get cancelled with 2 pi m. So from this you can see that, so what we get is sigma, that is of the order of delta over E. So this we write it here, delta over E V over h cube the power n, that is 2 pi me raised to power 3n by 2 over 3n by 2 minus 1 factorial. So this 3n by 2 when comes in the denominator, we know that the gamma function gamma of n, that is equal to n into n minus 1, or similarly gamma of n over n, that comes out to be gamma function of n minus 1, or you can say that n over gamma function of n, that is equal to 1 over gamma of n minus 1. So similarly, so this 3n by 2 when goes in the denominator, so we can write this as 3n by 2 minus 1 of gamma function. So this is our new microstate. So for this micro-canonical ensemble, so that is dependent upon this 4 parameter NVE and delta. So again, we have find out the total number of microstates. We have also find the value of this omega, that is the volume for this whole phase space hypershell, and from that we can find out the value of omega for 1 microstates. So we know that the value of omega, I will write it here again. So omega, which we have equation derived, so in this previous equation, so this is the value we have already derived. So value of omega naught, we know that is equal to omega over, so value of omega naught, that is equal to omega over sigma. So we need to equate these two equations, omega and sigma, and from that we can find out the value of this omega naught. Now I will write it here, the value of this omega, so which comes out to be, so when you rewrite it and try to solve the value of this omega is similarly in the notations which we have calculated for this microstates, and it comes out to be equal to v raised to power n delta over e 2 pi me raised to power 3n by 2 over 3n by 2 minus 1 factorial. So when you relate these two equations, so let us say this is equation number, so let me rewrite. So this is equation number 2 and this is equation number 4, and when we equate this equation number 2 and 4, and from that we can calculate the value of this omega naught, so that is equal to omega over sigma. So when you divide these two equation, equation number 2 and equation number 4, and from that what we calculate is, we calculate it comes out to be of the order of h raised to power 3n. So this is for the 3n dimensional hypersphere, so in which the number of microstates which are lying within the energy limit from E minus delta by 2 to E plus delta by 2. So similarly, if the system it is having studied for this n degrees of freedom, and when we derive that value for this n dimensional degrees of freedom, so then the value of this omega, it comes out to be of the order of h raised to power 3 for n dimensional sphere. So this is for the 3n dimensional sphere. And similarly for a single particle, if we consider for this one dimensional sphere which is having 3 degrees of freedom, then the value of this omega, so again it is coming out to be, so this is for h raised to power n, that is for this n dimensional, and for this single particle which is having 3 degrees of freedom, the value of this omega, that is of the order of h raised to the power 3. So this is for the single particle having 3 degrees of freedom. So the total number of microstates, so which we have derived, so that is equal to volume into 4 by 3 pi p cube. So that is, so p, if it is within this energy limit, p less than capital P, so for a free particle over, this is for single particle. So this is the total number of microstates which comes out to be, and it is generally defined as a summation, so that is dependent upon NV and E, and the number of microstates within this momentum, which is lying between P and P plus delta P. So this number of microstates, so it is given in terms of Gp dP, and that is equal to curly by curly P and summation of this total number of microstates, which is a function of momentum. And when we solve this equation, so this comes out to be curly over curly P, so 4 by 3 pi P cube. So this is the total number of microstates in terms of momentum over omega naught, so that is equal to h cube for one particle in having 3 degrees of freedom into dp. So when you solve this, so it comes out to be gp dp, so that is the total number of microstates within this momentum limit, so that is of the order of v over h cube 4 by 3 pi 3p square into dp. So that comes out to be v into 4 pi p square over h cube into dp. So this equation we will use in many of the cases when we will solve our canonical ensemble, and we will find out all these energy values in terms of momentum. And similarly, we can also write this total number of microstates in terms of energy. So number of microstates, so lying within this energy range, so that is between E and delta E plus delta E. So that is generally in terms of GE into DE. So again we derive that term, so that is the summation of E in terms of DE. And so here we will write all those momentum terms and we will convert those momentum terms into the energy equation, that is equal to E is equal to P square over 2m. So this equation comes out to be V over H cube into volume, so that is equal to 4 by 3 pi into P cube. So P is 3 by 2 into 2m E under root into 2m. So when we solve that, so our number of microstates in terms of energy GeDE, so this comes out to be V over H cube into 2m into 2 pi E 1 by 2 into dE. So this results they are hold or they are valid. So if the value of this V, so that is having very large value, or it is having a infinitely large value, and for the micro-canonical ensemble and the system, so in which the finite volume of this V, so that if V is very small, then these results they are not conserved, or these results they are not valid. So these results are only valid so if our micro-canonical ensemble, which is very large, and the system which is having this much volume, which is very large. So this is all about the classical ideal gas, and from this classical ideal gas we have derived this volume of this 1 microstate, so which comes out to be of the order of h raised to power 3n for this 3n dimensional hypersphere. And from that you can calculate all those other cases if you are solving this problem for this n dimensional sphere, or if you are solving only for this one single particle which is having 3 degrees of freedom. So these all three equations, they are quite important from numerical point of view, and you will use these equations when you solve these micro-canonical ensemble problems. So the similar relation we can also derive the same which we have derived for this classical ideal gas, the same we can derive for this linear harmonic oscillator problem. So the second example is of the harmonic oscillator problem. So let us consider a one-dimensional linear harmonic oscillator and for this the Hamiltonian, so that is the total function or the total energy of the system, so that is generally defined in terms of position and momentum coordinate, and that is equal to p square over 2m, which is the kinetic energy of this equation, plus half k into q square, where q is the momentum coordinate, and I will write all those other notations where k, that is generally known as the spring constant or force constant, and m, that is the mass of oscillating particle. So the space coordinate q and the momentum coordinate p, so of this system, they are generally given in this equation. So this q, which is the position coordinate, it is generally defined as a cos of omega t plus phi, and the position coordinate p, that is generally the momentum, which is m into x dot, or here x, that is the q value, which is the oscillator problem in this three-dimensional problem, so moving along x, y and z axis. So from this when we take this the derivative with respect to time, so this equation, so the q dot, that is curly q by curly t, so this equation becomes minus a omega sine of omega t plus phi, or putting these value of q dot in this equation, and we can write this momentum equation. So this comes out to be minus ma omega sine of omega t plus phi. So where omega, that is the angular frequency, so which is dependent upon this spring constant, so that is equal to under root of k over m. So once we find out the value of this angular frequency from these two position and momentum coordinate, from that we can find out the energy of this harmonic oscillator. So the energy of this oscillator, so that is 1 by 2 m omega square into a square, and from this energy we can find out the phase space trajectories of those representative points of these system, so that we can find out from this p and q value. So q, that we know, that is equal to a cos of omega t plus phi, and p we know, that is minus of a ma omega sine of omega t plus phi. So if we take the square of this q value, so q square, it comes out to be a square cos square omega t plus phi, and if we square this p value, the square of momentum square, so this comes out to be m square a square omega square sine square omega t plus phi. Now if we add these two equations, so that is q square over a square plus p square over m square a square omega square. So right hand side, so this comes out to be cos square plus sine square theta, so that is equal to 1. So this equation which we had derived from this harmonic oscillator problem, so this equation, it is the equation of ellipse. So you all are familiar with this equation of ellipse, that is q square over a square plus p square over b square. So that is equal to 1. So where a and b, they are generally known as the semi-major and semi-minor axis of this ellipse problem. So this is the value of a and this is the value of b. So that is the semi-minor and semi-major axis. So equating these two equations in terms of this ellipse equation, and from that we can write out this equation. So this comes out to be q square over 2e over m omega square plus p square over 2me. So we have written this equation in terms of energy values, and from that we can find out the value of this energy. So that we generally know, that is m omega square a square, and from that we can find out this a square is equal to 2e over m omega square. So if we equate this equation with the equation of ellipse, and from that we can find out the value of this semi-major axis, that is a square, which comes out to be 2e over m omega square, and this semi-minor axis, that is equal to b square, which is equal to 2m into e. And from that we can calculate these two axes of this ellipse, that is a comes out to be under root of 2e over m omega square, and b comes out to be equal to under root of 2m into e. And from that we can find out the area of this ellipse problem. So let me add some more sheets. Okay. So from once we find out the value of this a and b, so these are the values of a and b, and from that we can find out the area of ellipse. So that comes equal to pi into a into b. So this area, it comes equal to pi into a into b. So pi into a, that is equal to 2e over m omega square into under root of 2me. So this comes out to be 2 pi e over omega. So that we see that the phase space trajectory of these representative points of the system is ellipse with the axial representation. So that is it is proportional to E. So the area, it is directly proportional to E. And if we restrict these oscillator energy, that is from the sharp energy to E minus delta by 2 to E plus delta by 2, and the representative will be confined to the phase trajectories which lie within this region, which is bounded by these elliptical trajectories. And if we change these values, so they will be bounded something like that. So this is E minus delta by 2, and this value, that is E plus delta by 2, and this trajectory, so the particle which is lying within this trajectory, so that is from that we can find out the volume of this region. So since it is for a one-dimensional problem, so this will be equal to dq into dp, and this comes out to be equal to 2 pi over omega, and the value of E, so that is lying within this energy value from E plus delta by 2 to E minus delta by 2. So if we take 2 pi over omega as common, and from that once we solve this, so it comes out to be equal to 2 pi e plus delta by 2 minus of e plus delta by 2. So this e value they get cancelled, and what we get is 2 pi delta over omega. So this is the confined volume of this phase space trajectory region. So the area of a phase space trajectory, since it is for a one-dimensional problem, so the volume it is equal to the area of this phase space. So the area of phase space between these trajectories, so that is equal to 2 pi delta by omega. So where delta that is of the order of h bar into omega, because the energy value in terms of quantum, it is not a continuous value while it is a discrete value. So the value of this En for the quantum mechanics problem, it is of the order of n plus 1 by 2 of h over omega. So similarly the value of this delta, it is having some discrete energy value, and so the area of this phase space for this single harmonic oscillator problem, so it comes out to be equal to 2 pi into h bar omega over omega. So that comes out to be of the order of 2 pi into h bar. So for arbitrary value of this E and delta, the number of eigenstates within this allowed energy region, it is very nearly equal to delta over h bar omega, and the value of this energy, it is lying within this energy range from E to h bar omega, and the value of this delta, which is very small with respect to this energy value, and this value it lies between these two limits. And so the area of phase space per eigenstate, so it is generally given as the volume of one microstate or the area of one microstate, because we are solving this problem for a one-dimensional motion. So that comes out to be 2 pi delta over omega and delta bar over h bar omega. So this comes out to be 2 pi h bar, that is equal to of the order of h. So this is for one particle moving along having 1 degree of freedom, because the oscillator problem, it is only oscillating along a particular axis. And if we solve this harmonic oscillator problem for this single particle along this three-dimensional, then the value of this omega, it is coming of the order of h cube. And similarly you can solve this for n-dimensional and three-dimensional problem. So this is all about this micro-canonical ensemble, and in our next lecture we will discuss about the canonical ensemble, and from that we can find out what is the difference, major difference between this micro-canonical and canonical ensemble, and we will derive the relation for partition function. So okay dear students, if you have any doubt you can write in the comment box, or you can also ask me on WhatsApp. So I will also share all these notes on this WhatsApp group. Till then, goodbye. See you in the next lecture.